Yeah, good afternoon and welcome to the Communication Signal Processing Seminar. As This semester is all virtual and it's likely to be the same next semester as well. Um, so first, I
Yep.
did want to thank a few people, I guess well, the supporters, which are the KLA and the two research groups, NCIS and SIPML. And I'll also I say mention it every time, and I think it's not enough, is to thank Shelley for all the coordination activity she does behind the scenes. So
Yes.
she deserves more credit than what I can give her in this. So anyway, so we have a speaker, Mike McCann from MSU, and Jeff is going to be the host, and he's going to introduce him. So Jeff,
Uh,
go ahead and take the lead.
okay. Welcome, everybody. It's my real pleasure to introduce Mike McCann for today's CSP seminar. Mike is actually went to Michigan as an undergrad. I think he got his bachelor's degree in biomedical engineering with a minor in CS back in 2010. And I think he reminded me that we met maybe back then, although that was a long time ago, because we were both collaborating with Jane Hungens at some point back there. Then he went on to Carnegie Mellon, where he got his PhD. Then he went on to do a postdoc at APFL in Switzerland, worked with Michael Unser, and did very influential work on applying CNNs to medical image reconstruction problems. In fact, the field is only a few years old, but he's already written a survey paper that has over 250 citations, and he was a co-author of one of a really seminal paper on applying CNNs to, let's say, denoise images coming out of a CT scanner. That has, I don't know, 800 some citations or something like that already. I was thinking about that, like a great way to get a paper a lot of citations is to write a paper that is seminal, one of the first methods in the field, but make it a method that everybody else has to compare to and maybe is not too hard to beat so that they can keep comparing to your method and citing it, because that's the standard now. Every paper these days, people have to compare to this so-called FPP ConvNet that group developed. Michael was part of it. And then now he's a postdoc at Michigan State University, working in the lab of Sai Ravi Shankar, who was here at Michigan for a while as a postdoc. And so the work that Mike is presenting is a great interest to us, and we really look forward to your talk. So with that, Mike, I'll turn it over to you. Thanks a lot for doing this.
All right, thanks, Jeff, and thanks for everybody for tuning in. I will share. Okay, so I hope everybody can see slides.
Yep.
Okay, so I really have three topics together today that are sort of loosely unified by this idea of not enough measurements and too many measurements, which I will explain as we get into it. So up front, my collaborators on this come from two groups. So as Jeff said, with Mikhail Unzer's group, the big group at EPFL, and especially Kyunghwan Jin and Lauren Donati and Harshit Gupta. And then also work with the SLIM group in Sai Ravi Shankar and a incoming PhD student there, Farjeet Josh. So that's them. You can tell it's Switzerland in the top picture because of the mountains, and also because everybody's holding an alcoholic beverage at that lab meeting. Okay, so my research generally focuses on reconstructing meaningful images from their measurements. So what shows up in your scanner on your computer at the end is G, is just some vector containing a bunch of real numbers. And the thing we're interested in is, generally speaking, an image. So I'm using the term very, very generally. So some scalar quantity that varies with space and possibly time. This is what we want to sense. And mediating between those two things is the physics, which I'm putting in curly H here and with the curly braces to remind us that the physics is complicated. The physics isn't necessarily linear. And when you write it this way, the physics also includes the noise and sort of everything else. In fact, we can say we never really know this curly H exactly. But here's a very simple, almost sort of toy example, X-ray CT. So the thing we're trying to sense here is a function of two dimensions, X1 and X2. It's a very common phantom. And the way the measurement procedure would work is you take a line integral of this function, and that gives you a number. you can associate that number with a point in this line space. You just imagine parameterizing lines however you like. So you could parameterize it by the angle it makes with one of the axes and the offset from the zero line. So you get a number that way. And if you do that for every possible ray, you get this beautiful thing called a sinogram. And that whole thing taken together, you could think of as being the measurements. So this is the forward problem. And the inverse problem is the thing on the right shows up in your scanner, and you want to get the thing on the left. And so measurements, taking these measurements is in almost every domain expensive in some way. So I don't mean necessarily in terms of cost, although it could be in terms of actual dollars, but generally in terms of the time it takes to gather measurements like an MRI, or the radiation exposure to the patient, or numerous other things. So we generally, if we think of a discrete problem, and here I'm now writing a linear problem, discrete finite dimensional. If you think of getting M measurements and you want to recover N elements of your image, we'd like to take M much smaller than N in many modern systems. But I mean, you know, if you had your linear algebra class, you'd say, well, it's impossible. You know, you can't invert this thing. I'm writing here a linear system. There's more unknowns than you have equations. And so you can't do anything. Now, circa 2008 to 2016, there would be a next slide here. And I'll give like 10 seconds for you to just think about what would the next slide be here after they say their problem's impossible. Okay, I don't know if this will ring a bell for anybody, but the next slide would be Sparsity to the rescue. And they would show this little graphic. I won't explain what this thing is because that's not the story I'm telling today. I think that's a great story, but we're gonna say something different. So today I'm gonna say there's hope because we actually have, in another sense, we have too many measurements. Well, what do I mean? Well, there are these databases online. So this is a big one, the Cancer Imaging Archive. And I don't know how big this is on your screen, but over here you can pick a modality. There's MRI, there's a bunch of other things. You can pick organs, and there's just scans upon scans upon scans. So this is 2,000 subjects, hundreds of images per subject. So if you want, you know, if you're trying to do CT reconstruction, there's tons of CT measurements out there. Of course, they're not of the data that you actually have, right? But you have all this data sitting there, and maybe we can do something with that. So I like to think about that as sort of reformulating the original problem. So down in the lower right, that's the problem I was saying before. You know, okay, we have G, we want F. But there's this other thing floating around, which is these pairs of images and their measurements. So the question is, what can we do with this thing? Okay, so when you write it like that, it puts you in the mind of doing what I'll call supervised image reconstruction. So just to parse this a little bit, F hat is our estimate of the image. This is what we're trying to recover. And we're going to write that, like our algorithm is going to be applying some F, which we're going to design, but the F is going to be parametric. So it's going to have a structure, but it's also going to have some parameters that we're going to think about varying, and it's going to get applied to the measurements. And we're going to learn, trying to taboo the word learn, but let's say learn or fit that theta as another minimization problem. So now we're going to say, I have some measure of distance or displeasure, and I'm going to compare ground truth images from my training set to the reconstruction of their measurements with my current thetas. And I'm going to try to find a theta so that those reconstructions are always close to the ground truth. So I think there's immediately a bunch of questions about how you would actually do this in practice. So what do you do over here? What do you pick as your distance on the right-hand side? Well, you know, everybody uses MSE, or maybe they use absolute error. This is kind of easy. The second bullet, where's the training come from? Well, there's actually lots of training, as I said, and you could, in certain modalities, you could kind of make the training data yourself. If you assume H is completely known, then you don't really need paired measurements. You just need the Fs. So, well, I shouldn't say these things are easy, but I think there's at least obvious solutions to the first two. The third one, how do you solve the fitting problem? Well, stochastic gradient descent. Although, you know, there's a huge field of research around how to do that really efficiently. But I think most of the innovation for us doing biomedical imaging is, I mean, with respect to this kind of formulation is, what is the structure of this F? This is completely wide open question. I mean, you can essentially put anything you want there. So this is probably outdated by now. You know, I've tried to write a review paper of this, and it's the field moves so quickly that you really can't say anything that's really correct, and you're always leaving somebody out. So, you know, apologies if I'm leaving you out here, you can tell me. But some major themes in what you use as that parametric function. And of course, one major theme that's not written here is it's usually a CNN of some kind. Okay, but within that class, you could take a direct method. So I haven't really talked about these, but you know, in the very old days, you just wrote down on a sheet of paper some kind of an inverse or some kind of regularized inverse, and you just implemented it in your computer. So there's no real optimization problem. There's no learning. It's just a one-shot thing. So you could take some of those one-shot things that already exist, and you could try to kind of tune them up a little bit. So there's people doing that back in 2013. We have this FBP ConvNet thing, which Jeff mentioned, which is you could say, well, take a direct method like filtered back projection, and then let's use a CNN to kind of clean it up at the end. You could also take your favorite variational method. So I use the term variational several times here. To me, this means just solving an inverse problem, solving an optimization problem. Sorry, let's say that, solving an optimization problem. So like calculus of variations, but this is just, I mean, just argmin of stuff. So you could take your favorite optimization formulation for doing image reconstruction, and you could try to turn it into a neural network somehow. And many of these things involve filtering, and we talk about this actually in the FBP ConvNet paper as well. But you can view many of these things as sort of already being a convolutional neural network. And so you could, there's kind of this duality, and you think, well, I'm just going to tune these things up in some way, learn the effect of the regularizer, learn gradients, learn filters and nonlinearities, and there's bunches of ways of doing this. You can also throw away direct methods, throw away variational methods, and just say, I'm just going to take a huge CNN, just going to go, measurements are going to come in this side, images are going to come out the other side. And, you know, this is this Nature paper that everybody cites. Then there's still yet other things you can just try to, in many of these cases, it's like, you can think of the few measurement problem as there being missing measurements. There's obviously measurements in places, you'd like to have measurements sort of everywhere, and you don't have measurements everywhere. So you could think of that as an in-painting problem on the data domain side, since people doing that, and there's tons more things. And I'll show a typical result that's from our work, and Jeff took the words out of my mouth. I mean, we see in postdoc, a good way to get a paper cited a lot is do something reasonable and make it really easy to beat. And that's FBP ConvNet. So I think people feel they have to compare to it, but they're sort of happy to compare to it because they know they're going to beat it. Anyway, so here's a ground truth. This is an image. The next row is what you get if you apply a direct reconstruction, so kind of old school reconstruction, to the undersampled CT data. You get these characteristic line artifacts. The third column is what you get if you do total variational reconstruction. And I tuned this as carefully as I possibly could. So I think this is the best result you can get out of TV on this data. So you could think of this as sort of representing compressive sensing. And the last row is what you can get. And the last column is what you can get using a CNN to denoise the second column. And depending on the contrast of your screen, you may not see very many differences between these things, but the textures in the right-hand side they're a little more believable. TV tends to have this sort of, people call stair-step artifacts. It looks a little cartoony. And you also avoid all these lines that you get in FBP. So I'll just take a second to say a few things about all of this. The talk isn't really about this exactly, but I think when reviewing these papers and when thinking about this, I think it's very important to remember that there's sort of the inverse crime version of the problem. That's where you assume H is perfectly known. You also tend to assume that it's linear. And you also tend to, have your own noise model. And that's what we did in the FBP ConvNet paper. But in the real world, you care about H. You care about this curly H, the stuff that's actually coming out of your scanner. And I think that in the variational world and when you're doing direct methods, the difference between those things probably doesn't matter too much. But when you start fitting data, you can fit things about H which are not going to be represented in the curly H. So, well, you can ask me about that, but I've observed that at least in some cases. This is something you have to be really careful about. And I just want to say that there's significant engineering effort that goes into getting things to work on real data. And I think if people are doing that in the papers, they should be rewarded for that. And they should also make a big deal about it. The second one here is, I somewhat get the feeling we're moving into a regime where you just want to have a bold number in a table. That is, you want to have the best SNR, the best MSE. And maybe in the past few years, everybody rolled their own data sets. So there's no way you could compare, and everybody claimed to be state of the art. This is kind of impossible. So I think that's a fine kind of research, but let's actually do challenges, right? Let's make apples to apples comparisons between people, and we can start figuring out what's really working, what's not. But the last one is, it's not all about MSE. I mean, it's fine to try to invert matrices. That's a good problem, but we ultimately want to do medical imaging. So here's an example from FPP-CommNet where the ground truth is on the left. There's a little piece of bone, I think, something that's meaningful. And the FPP-CommNet result, although it's better than all the comparisons in terms of MSE, it just deletes this bone completely. So you have to try to reconcile, is this bad? Because the MSE is better than everything else we tried. So it's sort of, by that definition, it's good. But I think you'd be right to be a little uncomfortable about these kinds of things. So not actually sure data fidelity would correct that, but this, broadly speaking, I'll say this is robustness. Okay, so a very brief summary so far. If you have a lot of measurements, inversion is actually pretty easy in many cases, and it is the case in X-ray CT. You don't need to do anything fancy if you have plenty of measurements. If you don't have enough measurements, so here I'm representing that by, this is a downsampling, so I'm throwing away columns of this thing. That's really, really hard. It's underdetermined. There's infinite number of solutions that all have the same data fit. So you kind of need to bring something else to the problem. What you bring is all of this training data, you have supervised low dose X-ray CT problem, and that's kind of doable. And now the next topic is, it's a topic where actually you have tons and tons of measurements. And you could start, this is like where they slowly revealed a picture of the Pokemon or something. I don't know if anybody knows what I'm talking about, but try to think about what is this application? You have tons and tons of measurements, actually way more than you need, but they're all jumbled up. So you no longer know the X direction here is the angle. You no longer know what angle your measurements came from. You say, okay, that's pretty bad. And the SNR is about 0. So the data really looks something like this. I'll show you in the next couple of slides. So I don't know, does anybody have it yet? This is cryo-EM. So cryo-EM is a way of imaging biomolecules, small biomolecules of proteins. And what you get is, I'll bring up the image. You try to make a monolayer of your molecule in ice, and you image this with an electron microscope. And what you get is random orientations in 3D, which means you get random projections on your microscope. There's electron optical effects, which I'm not really going to talk about. And the SNR is incredibly low. But in some sense, you can have as many projections as you want. I mean, the way that experimentalists talk about this is it's kind of like, they can give you 1 million projections or more. It really doesn't matter. I mean, so let's see. Now, this diagram is a little bit misleading because it's like you're looking at the molecules and they're casting shadows. And that's really not exactly what's happening. It's really that, putting optical effects aside, the cartoon of this is that the molecules are absorbing electrons, and therefore those electrons aren't making it through to the other side. So you have to think of them as sort of like little clouds. And so what you get is these actual projections. So the difference here is, a shadow is just black, a projection is a projection. It's a line integral. But this has resolution that is, to me at least, unbelievably good. So there are labs that are claiming 2 angstrom resolution. And at that resolution, you can see, so look at phenylalanine, you can see hexane rings, in your reconstruction. So the ball and stick model is added later, but this wireframe is a level set of their reconstruction. So it's still not obvious to me if this even should be possible, but here it is, the papers exist. Okay, so going back to this equation I started with, so now what you have is, you have plenty of measurements, but you have some unknown, essentially you could think of this as being the forward model is unknown in a really meaningful way. That is, this theta would encapsulate all of those 3D poses that you don't know. And so I think there's 3 big classes, or at least we identified 3 big classes of ways of solving this. So I think of the first one, projection matching, as sort of the engineer approach. I don't know a volume and I don't know a pose for all of my projections. What do? Well, I'm an engineer. I estimate the volume. I use the volume to estimate the poses. I use the poses to estimate the volume, and I go back and forth. So the problem with this is that the more and more data you have, the more and more poses you need to estimate. So somehow this doesn't feel right, because you should think in the limit of infinite data, the problem should eventually get easy. The next way, and the way that all the software, most of the software that people actually use to do this in the lab, the way that they do it is marginalize maximum likelihood. So you marginalize over the poses, which seems to be, sort of the statistically correct thing to do. The problem is that ultimately involves projecting your molecule at a bunch of different angles and computing distances to a whole bunch of different projections. So you need tricks there to make this thing computationally feasible. And you obviously have to grid rotations. So, there's some trade-offs here and all of this. But anyway, this does really work, and you can get down to these single-digit angstrom resolutions. Then another one, it's interesting here, so a reference from 1980 and a reference from 2020. So I learned about this kind of from the 2020 reference, is the method of moments. So what you can realize about the X-ray transform is that their moments of the projections will put constraints on moments of the volume. And the simplest one to think about is that the mean of the projection and the mean of the volume need to be the same thing. So if you have one noisy projection, well, it's pretty hard to estimate the mean because it's so noisy. But if you have 1 million noisy projections and they all have the same mean and it all equals the mean of the volume, you can estimate that mean very, very accurately. And so you actually, you know with almost certainty the mean of the volume you're trying to reconstruct. Well, that doesn't really reconstruct you a volume, but if you could do it with more and more moments, then you can start reconstructing an actual volume by searching for a volume that has all of these moments equal to such and such quantities. And the really nice thing about this is that when you make these estimations of the moments, the more and more data you have, the more and more accurate you are. So it has exactly this nice quality that you sort of using the data efficiently, and you like to have lots and lots of data, and you're averaging things, you also not doing any of these parameter estimations. So I think this is really great. When I read these papers, I think, yeah, this is what everyone should do. This is not what people do. That's sort of a mystery to me. So, maybe there's issues getting to this to work in practice. So we came at this from a different direction, and it came from thinking about GANs, generative adversarial networks, which are also sort of, everybody does a CNN first and then they do a GAN for their next thing. So I just briefly talk about GANs because probably everybody's seen GANs, but so the idea of a GAN is you give the algorithm samples from a certain distribution, potentially a very complicated distribution, like the distribution of images of digits of a certain size. And what the algorithm does is it trains for a while, multiple days maybe, and then it gives you a way to generate new samples from that distribution. So this image is samples generated by a GAN from the distribution of handwritten digits. The right-hand column is the closest digit in the actual training set. They're trying to prove that they're not just copying the training set and they're getting something new out. So this in and of itself is pretty remarkable, but it's sort of not actually the thing that makes this useful for cryo-EM. But what's even maybe more impressive about this is that the parameterization of that generator is completely flexible. So you can, however you're making these images, you sort of get to pick what the architecture is that makes these images. And the algorithm will try to do the best it can with whatever architecture you give it. So you'll see this in a couple slides, how we make use of this. So in a typical GAN, you have two networks. And I think the easier one to think about is the discriminator. It's really just a classifier. The job of the discriminator is give it an image, in this case, face images, either sampled from real faces or somehow faked by some generator, which I'll describe in a second. And the discriminator just has to say whether this thing is real or fake. And this is just a completely normal classification problem updated in the normal way. So then the question is, well, where are these fake guys coming from? So the fake images are coming from some generator. And the typical way you do this is you take some random Gaussian noise, you put it through a bunch of convolutions and nonlinearities, and the output is an image. So it's great, but how do you get these weights? Well, you get these weights by imagining you have this fixed discriminator that does what it's supposed to do, and you train just to try to fool this thing. So I think this is sort of like what I was speaking about before. If you have a fixed discriminator that does its job, it's easy to train a generator. And if you have a fixed generator that does its job, it's easy to train a discriminator. Now, training both of them at once, it's not so obvious, but you're just going to do the same thing. You just alternate between the two of them and you hope that you converge. So, okay, well, how do you do this in cryo-EM? Well, the obvious thing here is you put your projections here. So instead of faces, we have projections, and you have the same generator. And so you make these fake projections. And as I say, this would be like this projection does not exist.com. And this is not obviously useful. So think about what this gives you is a way to generate things that look like projections. It doesn't reconstruct anything. And we already said that we have as many projections as we want. We don't need any more projections. So at this point, what we want to do is make use of the fact that the parameterization of the generator, like this structure, is completely open. We can do anything we want here. So no one forces us to take random noise and put it through convolutional layers. So what we actually do is we parameterize the generator with a volume. So you can, if you want, you can think of the weights of the generator as actually being this 3D volume, this thing we want to reconstruct. And then the generator doesn't have all of these weighted convolutions and everything. It's just a forward model for cryo-EM. So interestingly enough, in the previous case, the randomness comes from the input, and the generator, the thing you think of as the generator, is completely deterministic. If you take the whole thing as a unit, of course it has to be random, otherwise you'd always get the same image out. So again, if you take this whole thing, the deterministic part is this model, but the model involves randomly sampling angles. So you still get something that makes you new projections. And if you want new projections for some reason, you could use this model to do that, but that's not what we're interested in. We're actually interested in what weights it learns, that is, what volume it learns in order to efficiently make those projections. So I'll just show quickly some results for this thing. So I can say basically, this is not going to give you 2 angstrom resolutions like people are using in the labs right now. So no one's going to throw away the software they have right now to switch over to this. But the thing does work, and it gives you some very interesting flexibilities, which, okay, I don't have a slide about this, but it gives you some interesting flexibilities in terms of how you parameterize the volume and what physics you can include in your forward model. And while working on this, it was sort of fascinating that there was sort of this interesting property where things that seemed like they would be hard when you're doing the maximum likelihood can be surprisingly easy in the GAN, but things that are easy in the maximum likelihood can actually be really, really hard in the GAN. So you kind of have this duality, and it's not exactly clear what's better. But anyway, the thing works. So I just quickly show the results. This first figure in the upper left, this is showing projections that are coming out of the GAN as it trains, and it's always at the same angle, and we're not showing any noise on these things. And I guess the point of this is that it pretty quickly converges to something that's making kind of reasonable projections. And after some hours, you get projections like these. The CTF is these electron optical effects. So this is a necessary part of the forward model. And then you have to put noise on it. So this is the actual simulated projection images. And the bottom are the real the real projection images. As you can see, I'm not kidding about the level of noise here. I mean, it's a very challenging modality because you're not even sure if you're looking at data or just noise. But, in a sense, the whole idea here is, well, if the top row and the bottom row are indistinguishable, then you probably have a pretty good reconstruction. And this is a level set. So what we're reconstructing is a 3D volume of pixels. And what we're showing is one level set of that thing as it progresses over training of the GAN. And so, of course, this thing is, you can quantify resolution somehow. It's sort of contentious, but it's some, a few angstroms. And you can see that it's kind of getting close to the ground truth. Should also mention that the symmetry here is enforced in the algorithm, so it's not discovering the symmetry itself. So yeah, the thing works. It gives you some really interesting flexibility, and I know that Harshit is taking this forward and doing some extensions. I think he already has extensions out there, so you can ask me about that if you're interested. You can also, there's a space webinar video about this by McCann. So if you want to see more cryo-GAN stuff, you can see my old boss talking about cryo-GAN. And if you don't know about space webinar, it's really cool. You should check it out. Okay, so those are the first two topics. I'm going to take an intermission and ask if there's any questions, burning questions now about those topics before I launch into the third one. And I mean, you can ask at the end as well. It's fine.
I'll ask one. It would seem like with the amount of noise in those projection views that it would be quite easy to fool the discriminator, right? How can it reliably discriminate true and fake projection views given that degree of noise? Is it especially hard to train because of that?
It is especially hard to train, and it's not a priori obvious that this thing would work at all.
Yeah. Okay.
But I mean, we should also say some other things. So it's very hard to look at the images, but if you take these images and you do like block averaging in groups of 8 pixels or something, you do start to see structures. So it's not quite as dire as it can look.
Okay.
So I think that may be what the discriminator is looking at. But in question about how you could recover things at a resolution similar to the pixel resolution I think is still open, and I think is still open in the cryo-EM field kind of more generally. So there's a paper that's sort of famous to all those guys called Einstein from Noise, where they, because there's a lot of, let's say, dirty tricks that you need to use to get these kinds of, 2 angstrom, insanely accurate reconstructions. And there, a group said, hey, look, I mean, if we can take something that's actually noise and apply all these dirty tricks and we get beautiful reconstructions out. It's also a little dangerous because in many cases, you already know what you're trying to image. So yeah, you can think about how that biases your algorithms.
Yeah, even knowing that it's symmetric means you know something about the molecule in question. Or whatever. Yeah.
But in these cases, the secondary structure. You may have a good guess at the tertiary structure. So you're really like, these guys know that there is a hexane ring right here.
Yeah.
That also, by the way, probably informs their choice of which level set. Like they probably picked a level set so there would be a hole in the middle here, which I don't blame them. I mean, we do exactly the same thing. But remember, this thing is a density. It's a function of 3D space. So there's no edges here really. Yeah.
Great. Thanks.
Mike, can I quickly clarify 2 things? The first is that So you, for every reconstruction that you're trying to do over here, you have to train your discriminator from like the scratch in your.
Exactly correct. Yep.
So in that case, does that mean that your discriminator in this map is acting as your data consistency of some form? Like that's the substitute for data consistency? Like,
yeah, I think you can say that. I mean, because the only feedback that the generator gets is through the discriminator. So the generator has no access to the data set. So yeah, whatever data consistency there is happens through that feedback.
I see. All right.
All right. Okay, so we're going to return to X-ray CT for a little bit for the last subject here. So this is the figure that I didn't show. This is in the paper, but you don't show this figure usually in talks. So it's the same setup, but it's a synthetic experiment with these ellipsoids. Again, when you have few measurements and you do a direct linear reconstruction, you get all these horrible artifacts. But when you do total variation on this, you get incredibly good results. In some sense, the original paper is talking about, well, the original paper was talking about compressive sensing and total variation, showed things very much like this. In fact, you can get provably, well, maybe we can argue about whether the theory actually totally fits up. But that paper shows essentially perfect reconstruction of ellipsoids using total variation in a compressive sensing style reconstruction. So it's not surprising to us at all that we get really good results here. And FFPCompNet, the CNN, kind of struggles with this. And the reconstructions are, well, good, better than direct methods, but not exceptionally. So, this may be because Zhonghua didn't spend a week trying to make this better. But, when we had this, we felt kind of comfortable with this. But then in the same year, Ozanaktem's group published another CNN type method. And they, of course, compared to total variation denoising or total variation reconstruction. And they show that their learn method is pretty significantly better. And when I saw this, I emailed them about it. And I said, no, it's because you're using this anisotropic TV. You see the blocking artifact. So they're just doing up, down, left, right. And I said, no, fix it, and they said, yeah, we fixed it. The same result. The CNN is better than total variation on a piecewise constant phantom. And it just seems a little odd to me because, there's this kind of people say, yeah, TV is sort of optimal for piecewise constant. It kind of looks like it should be. So it's kind of rattled around in my head. So, and one way to attack this problem is I said, okay, well, remember the supervised reconstruction here. What if for our F, we just use this good old fashioned compressive sensing style or sparsity promoting regularization. So that's this minimization here. So you're minimizing a data fidelity term and a regularizer. There's a one norm. So you're promoting sparsity of WX. And for TV, W takes finite differences. But you could ask, well, maybe finite differences somehow aren't optimal. Maybe there's something better I could be doing than finite differences. Or maybe you like wavelets, but maybe there's something better you could do than wavelets. So let's use this whole guy as our reconstructor, and let's make the parameters this W. So you end up with this two-level problem. So you're going to reconstruct. X star is your reconstruction. Sorry, I'm switching from F's to X's and from G's to Y's, but I think it's kind of okay. And the parameters of this thing is going to be the regularizer W, so matrix. And you just have a sparsity promoting optimization problem. And then the way you're going to train this thing is you're going to try to look for the W star that minimizes the error on some testing set. So fine. So just to say, why in the world would you want to do this? Well, it can't be worse than your favorite sparsity promoting reconstruction. So I mean, so long as you can write it in this form, because if you have a favorite W, well, I can just initialize my algorithm at your W, and either yours is already local minima, or I can improve it. So you can't be worse than any particular choice of W here. In the end, after you train, the way you reconstruct is just by solving this inverse problem. So you don't have to worry about any of these like adversarial examples or anything like this, because I'm just solving a convex problem. We have tons of theory. You can talk about, continuity of this and all this kind of stuff. And maybe taken another way, you could say, well, this architecture, if you think of this as a sort of if you really blur your eyes and say this is some kind of a CNN, which is really not, but I mean, if you think of this as an architecture for these kinds of algorithms, this one works really well. I mean, this does lots of good stuff. So you're combining that, but you're also getting data adaptivity. I'll say one more point about that at the very end. And let's see. And the last thing is that because we're just learning a very small piece and we kind of know what we expect that piece to do, sort of like, I think this piece has to really sparsify X in order for it to be good in this formulation. So we know what we expect this guy to do, and you can really like look at what this guy does, and maybe you can try to make sense of it, which might be a little easier than trying to pick apart your CNN. So we're not the first people to write that thing down. So there's a bunch of related works on trying to do that. And all of the ones that we could find, they relax the L1 term and do gradient stuff. So actually, I'm just going to skip this, but I'll just say that. I mean, the only thing that makes this hard is that you need to compute gradients through this argmin. And so the non-differentiability of this term is really the challenge. And if you replace that term with some surrogate, then that problem goes away and you can just do first order optimality and you get your gradients. It's kind of okay. But we're going to take a different route. We're going to try to leave this unregularized. So I'm just, it's not a new equation. I'm just forwarding the old equations here. And I hope people have sort of had time to parse these. What we're going to do is gradient descent on the top problem. The way we're going to do that is we're going to start at some initial W. W is what you're trying to learn here. We're going to solve the lower problem at that W. And then we're going to try to find a closed form solution. So we're going to try to express X star not as a minimization problem, but just as some, we hope, linear expression. And of course, you can't do that in general, but we don't need to do that in general. We just need to do that locally around the W where we currently are. So we have some crazy function. We're at a point, we get a local approximation. Well, it's actually not going to be an approximation. We get an exact representation of that function that only holds locally. Once you have that, well, you're kind of done. I mean, you just need gradients of the top problem. The top problem is, the only complicated part about the top problem is the existence of X star. So really getting gradients of X star with respect to W is the hard part of all of this. Getting gradients of this whole quadratic loss with respect to X star is easy. So, chain rule gets you there. So that's the basic outline. Now, a few details. So solving the lower level problem. This is a standard convex problem. Of course, lots of people have solved this problem in many ways. I would think of ADMM and Chambol-Pak as sort of the go-tos for this thing. So in some sense, it's easy. The only tricky part in the problem that we're looking at is, I don't know if I'll really explain this completely, but well, you definitely need fast solutions because you're going to have to solve this problem thousands of times during training, probably, conservatively speaking, maybe more than that. So you really want an efficient implementation of whatever solver you're using. The other thing, maybe we can get around this with theory, but we haven't yet, is you need very accurate solutions to this thing. Because typically you could just do ADMM like 10 iterations and you get something and you don't even care if it's completely converged because the result, if it looks good and it has a good SNR or whatever, you're happy. In our case, you can't settle for that because if you don't actually solve the problem, then your gradients are wrong. And so you can diverge. So you need fast, accurate solutions. The one more thing that makes this hard is you don't need a fast, accurate solution for one Y and one W. You need to get fast, accurate solutions where W is changing and where you have potentially numerous Ys. Y are the training measurements. So you need to be able to solve this over a wide range of problems. And that's sort of non-trivial. So if anyone has suggestions, if you say, hey, I have no hyperparameters, it always solves this guy really accurately, I would love to hear about it. But let's assume you can solve that accurately. So I hope, oh yeah, I was thinking, oh, somebody's going to be really upset if I don't mention this. So all along I've been writing this x star, this is just a vector. It equals the argmin over x of some functional. But there's no guarantee that the minimizer of this thing is unique. And I mean, there's plenty of cases where it's not unique. So what do I mean when I write this equality? I mean, so the thing on the left is actually a set. And now I'm talking about taking gradients with respect to a set. So I hear you. If you're screaming in your head, like, no, this makes no sense, wait a little bit. It'll maybe get a little clearer. We'll be engineers and just march forward. So to boil down maybe a page of stuff into one sentence, the key idea here is that in a certain region of W space, so I have a parameter W, I'm at a certain W, and I'm looking around in that neighborhood. If the pattern of signs, and what I mean is whether you're positive, negative, or zero, if the pattern of signs of W multiplied by x star of W, and I'm just dropping the dependence on Y, let's just assume we have one Y. If that thing doesn't change in a certain region of W space, then this one norm term that was such a problem is really just a linear, it's just a linear term, because where Wx is positive, the one norm does nothing, and where Wx is negative, the one norm inverts the sign. So locally, the problem is not that hard. It's just a quadratic plus something linear. So in the archive paper, which is in my references, which you can see later, we take this idea and get closed form solutions in the case of the forward model being the identity. So that would be a denoising problem, essentially. And we do that by transforming, sort of boiling that problem down, making transformations until there's something we can write KKT conditions for. So I'm not intending that you read every symbol here, but only to say we basically have A, Z equals B, and the solution that we want is a subvector of Z. So that gives you a way of getting your X's by inverting this A, applying to B, and taking out the subvector you want. There are conditions on this thing because you start talking about inverting matrices, you worry. So there are situations where this is not invertible. And that was something that always bugged me. After putting this on archive, we found this great paper, which is again in the reference section. This is called something like The Uniqueness of Generalized Lasso. And this is even better than what we have. So sorry for the change of notation here. So what we call X, they call beta. What we call A, they call X. What I call W, they call D. So again, I'm not expecting you to parse everything here, but they do this. They characterize all the solutions. So this thing holds unconditionally. And what it involves is projections onto certain subsets of rows of W. That's this projection on a null space of D minus beta, which is sort of similar to what happens in our expression, and it involves pseudo inverses of those things. So you have that, and then as you might expect, there's a plus B. This is characterizing all solutions, right? So you get to pick any B inside a certain null space, and you get a solution. And what's nice about that is, going back to uniqueness, if you take B equals 0, then you get the minimum norm solution to your denoising problem, or sorry, your generalized lasso. And that thing's unique. So just throwing B away from here, you get an expression. This is exactly the thing that you would want to take gradients of. So that we now have two different closed forms, and they're the same in the cases where they should be the same. There's no funny business here. All that's left now is find the gradient. So with 1D signals, PyTorch, you could basically type this thing into PyTorch. You have to figure out, oh, what does this mean, project out of the null space of something, but you can basically type this thing into PyTorch. That pseudo inverses just involve SVDs, and SVDs are differentiable, at least some places, all the places that they kind of need to be. You could do that, and you can just get your gradients directly. And there's another nice work that we discovered. This is from Stephen Boyd's group. And they actually, so there's this great Python package called CBXPy from that group, as I understand it, that it's a modeling language. It allows you to type in problems like the lower level problem. It lets you type in that problem in some language, and then it just gives you a solver for it. And they have a extension of that where you type in a problem like that, and it gives you a solver for it, and it gives you the gradient of the argmin with respect to whatever parameters you want. So in some sense with that, I mean, this stuff's kind of trivial. I mean, somebody should just go and use this for biomedical image problems, right? So, well, it's not so easy. So with images, things get tough. So with images, this operator sparsifying transform, if you want to write it as a matrix, well, it's 1,000,000 by 1,000,000. So you're going to have problems there. This means no more SVDs, no more inverses, and CBXPy maybe can do stuff with images, but it's really, really tough. And so, you know, you don't have these easy shortcuts. And so we work out a solution for this in the paper, again, back in this case of denoising. It boils down to doing some sort of nasty matrix calculus by hand, and then you reach a point where all the pseudo inverses or all the inverses are gone, and then you can use PyTorch from there on out. So that's basically what we do. I'll show a couple results and then a wrap up. So we were doing image denoising. Again, I said W is 1,000,000 by 1,000,000, so you can't really parameterize W just by all the entries of the matrix. So you also need some way of parameterizing W with fewer parameters. And we do that by expressing W as a set of 8 3x3 convolutions. So the parameters of W are the impulse responses. There's 8 3x3 images. And that's the entire parameterization of W. And if you want to imagine the giant matrix is just those impulse responses repeated over and over again and shifted. But you never have to form that thing. We compare that to BM3D and then some 3 other sparsity-based variational approaches to denoising. So TV sparsity, DCT sparsity, and also trying to learn a sparsifying transform, but learning it in an unsupervised way. So you only look at clean images. And we train with SGD. A very nice tip that helped a lot in this project is don't decrease the step size, increase the batch size. There's a paper with that title that explains why you'd want to do that. It sounds very counterintuitive, or at least it did to me, but this I think is a nice and enduring trick in these kinds of problems. So doing that, you can get something that seems to kind of be learning something within a few hours. So the big results table. So maybe we'll start at the table at the bottom. So you have 15 decibels for your noisy images. And all of these things get you up to low 20s. And doing it with supervised learned, the thing I just described, can be a little better than everybody else, which is sort of promising. Like BM3D is pretty hard to beat in general, at least it used to be. TV should be pretty hard to beat on images like this. So sorry, these are the images we're denoising, so they're piecewise constant, and they're actually anisotropic TV should be really good at this. They just have horizontal and vertical edges. We'll dig into a few special cases. So here's a comparison. So top row is total variation denoising. Bottom row is denoising with the result of this learning. And in this case, for this image, they have the same SNR, but TV has these, so noisy image, result of denoising in the middle, right hand is the error image. And TV has a characteristic kind of distracting stair-step artifacts. And the supervised method, it's sort of the same accuracy, but it seems to avoid doing those things. You also note that the error, at least to me, looks to be axis aligned, more or less. So it seems like those filters are kind of starting to try to enforce structure like longer structures than TV is. Because TV, I'm actually just using 2-point finite differences. So you could tell that it's not really looking for long edges at all. It just wants edges. DCT, so here you're saying that you want a sparse DCT transform. So it's sort of like just smoothing the thing. And that's what you see in the results, sorry. You kind of get a blurry version of the left-hand thing, and the supervised guy is much sharper, I would say. Much, of course. Well, a little. Then coming back to this point about we have some chance to kind of introspect. So we can actually look at those impulse responses. So these things, these 8 impulse responses, so these are 3x3 images, these are what we learned. These are the parameters of W. And so a DCT would look like this one, and the supervised one, it's initialized with DCT, so it shouldn't be too surprising. It looks a bit like DCT, but we note that it makes use of the flexibility it has, which is to say the DCT is orthonormal, and the supervised guy has no constraints at all. And the supervised filters are indeed not ortho nor normal. So you can, if you stare at these for a while, you can see that they are not all orthogonal to each other. For instance, that pair. So it's actually, maybe it's being recorded, it's dangerous to say, but we had reviewers say like, how do you know those filters are not orthogonal to each other? Which, you know, one of those weird reviewer comments, you just think, maybe you need to describe that a little better. But, you know, think of these things as vectors. These vectors are not orthogonal. I don't have the color bar here, sorry, but I mean, white is 0, and one of them, blue or brown, is positive, and the other one is negative. So, and they are not normal in the sense that if you look at the center one, it hasn't moved from DCT, but it's scaled. So it cares a little more about those crosses. And the left-hand side of both figures is the responses when you apply it to a clean image. I don't know how much we can take away from that, but we can do that. So anyway, so just taking a step back and thinking about kind of what this thing gives us. Well, there's tons of evidence that CNNs work well on image reconstruction. And I see that as there's two things you could imagine that's coming from. It's either the CNNs themselves, so maybe CNNs are magic, or that they have I shouldn't use the word magic, but they have an excellent structure for doing image processing. Or it could be that training is just a really good idea, and maybe it doesn't matter what structure you use. And there's a great line of research on this deep image prior idea, which is essentially throwing away the training. You say, I don't need training. The architecture of the CNN itself is actually what's giving me good results. And if you want to get started on that literature, there's a recent Minds seminar from Reinhard Heckel that goes into this. And I think, it's a nice starting point there. And you can see the learned regularizer, the thing I just talked about, as sort of being the dual. You say, okay, I don't care about CNNs, this deep learning thing, it's not that interesting to me, but I think training is a really good idea. So that's the perspective essentially we're taking here. And it helps you disentangle these two things. So what I really want to do, I guess it's sort of obvious, is I want to compare the learned regularizer to a CNN on some of these tasks. And that would let you know, okay, how much of my accuracy is coming from just sort of access to the training set. And, essentially if our old variational methods had access to training, maybe they'd be really good too. Or could be the other, that in fact, access to the training means almost nothing. And it's really like conv relu is like a really, really important architecture we should look into a lot. All right, on that note, I'll end. Thanks to everyone for their attention. Happy to take questions. Or I don't know if we do discussants next and then questions after.
I'm actually not sure. I see some clapping hands. VJ,
yeah,
do you
actually,
want to
we do sort of take the discussions before we go for questions.
Okay, thank you.
Just so that they can talk and then you can come up.
Okay, and I'll try not to take too much time so that we don't cut into the opportunity for other people to ask questions.
Yeah, I failed keeping it to 45 minutes.
Oh, am I sharing properly now? What are you seeing? Are
A
you
lot of
seeing
stuff.
the whole screen? Okay,
Yep.
that's not what I meant to do. Let me try that again. I'll do a little Zoom 101 here. I want to share this. Now you're seeing the right thing. And then I do a slideshow of this in presenter mode. Okay, so we, as I mentioned to Mike before the presentation began, myself, my two PhD students, Caroline Crockett and Claire Lynn, are the discussants of this. And Caroline actually presented the paper associated with the second half of this research in a research group meeting of mine. So we're quite familiar with that work and really looking forward to discussing it. I'll just, at a high level, we want to contrast a little bit more, because we weren't sure how much you would, the non-bi-level versus the bi-level approach to these things. And then we have questions about some of this. So these are some equations grabbed from work of another former postdoc of mine, Il-Young Chan, who's now a professor at University of Hawaii. Or at least this equation is, where we have some training images and we try to learn filters from those, okay? And of course, you and Sai have worked on this as well. And we wanted to compare that. So here, there is no upper level problem, right? This is just a sparsifying filter learning problem, whereas your sparsifying learning filters are designed specifically to try to do a good job of reconstructing or denoising an image, whereas these filters are simply designed to try to sparsify images in hopes that those will be good filters for solving a inverse problem or denoising problem. And what we found is that the choice of this regularization parameter makes a huge difference in the kind of filters you get, right? So we've applied that to, say, the CT image here, and if we set the filters, the regularization parameter fairly small, we get some filters that have some similarity to the ones that you've showed, right? Some kind of finite differency kind of behaviors. These are a little bit bigger filters. I think these are 5 by 5 rather than the 3 by 3. But if you set the regularization parameter larger, you get filters that I would have quite a bit trouble interpreting. But then you can take those filters, of course, and use them in solving an inverse problem, very similar to how you have, except that you're doing it jointly in the sense that you're really optimizing the filters for the solution of that inverse or denoising problem. And we do, as long as we tune that regularization parameter well, we do get improvement, as you would expect, in the reconstruction compared to handcrafted filters, right? Filters like total variation kind of filters. And let me see here. So now I'm going to now turn it over to Caroline and Claire to follow up on those remarks with some questions related to your presentation, one of which might have been answered, we'll see, but why don't you go ahead. Caroline, are you first?
Sure, I can start. Thanks so much for the talk, Mike. It's very interesting work. So you talked a lot about the bi-level problem and that you sort of came up with this interesting way to solve it, where you basically came up with the local solution in a closed form. I think the other ways I see in the literature for how to solve that problem, one is to essentially consider the lower level, the denoising problem, as if it were just a series of iterations, and then take the gradient over that unrolled method. And then the other trend I see is to do this sort of implicit differentiation where you sort of similar to yours, you have to find the actual solution, but using a gradient. So you have some sort of, corner rounded one norm, and then take the gradient with respect to that. So I guess there's sort of two follow-on questions to the different approaches to the bi-level problem. One being a high-level opinion question on whether or not you even consider the unrolled method to still be a bi-level problem, or is it sort of bridging on just being a CNN? And then the other question here is, you mentioned you have to find X star very, very accurately, and I'm curious if you have any idea how your method, how accurate it has to be compared to sort of these implicit differentiation methods.
Sure. Great questions. Thank you. You've thought about this a lot. I really appreciate that. Well, on the first question, it's not so much, it's not a question of what is or is not bi-level or something like that. I think those things are meaningfully different. So unrolling and what we're doing are really different. And the main difference in my mind is that when you unroll, you can go 5 or 10 iterations, typically. Maybe there's other stuff in the literature, but the problem here is essentially that to compute those gradients, every iteration takes some fixed constant memory. So you can't go thousands of iterations, I don't think. So you're sort of limited in that way. And so you're essentially asking, well, is 5 iterations of gradient descent the same as minimizing that problem? And I would say, well, no, they're definitely different things. But they may, I mean, unrolling may work really, really well. I don't know. So I'm not sure if that really answers the intent of the question, but yeah, I think they're different. I think they're both worth trying. I think that the unrolling, it's maybe less clear what you get out at the end.
Yeah, that's fair. Right. It's not the solution to an optimization problem. So I agree, it's less clear. Yep.
Yeah. And maybe I would say that when you unroll, there's these matrices that are like the gradient and the gradient of the regularizer, let's say.
Mm-hmm.
And when you learn them, you still call them those things, but actually everything is mixed together. So you don't know whether the thing that was the gradient of the data fidelity, after you learn it, it also does regularization. You know, everything is just trying to push your solutions toward good solutions. So in our case, it's maybe much more constrained. We've really boxed in the learning in one place, and at the end, we really kind of, well, I don't know. Maybe it could leak and try to do something for the data fidelity, but it's hard to imagine how that happened.
Well, there are different versions of unrolled. I think the question was about the version where you don't touch the data fidelity and its gradient are the usual ones. It's not like, I think in Lista they learned both, but we like our H matrices as well, and we don't want to throw those away. And so I think we'd only be learning things associated with what's the regularizer. Yeah.
I think the point remains, which is that whatever you learned could be trying to do data fidelity as well somehow. Or
fair. Mm-hmm. Yeah.
So is that okay, Caroline, on the first one? Or do you want to follow up?
No, thank you.
And now the second one, how accurately. So there is a nice paper, and we'd like to use some ideas from it, which actually turned this around, and they realize, I mean, this same fact, which is that all you need, okay, let's say this. One way to think about what I've just said is that all you need to solve this thing with perfect accuracy is the sign pattern. Because then the solution just comes from inverting some matrix or applying some pseudo inverses, so that you can do that pretty accurately. So there's a paper where they essentially run their iterative algorithm, and then they periodically have a way to check whether their sign pattern is correct. And if their sign pattern is correct, then they immediately get the answer. My algorithm doesn't currently do that. So, you know, my algorithm currently just runs ADMM as long as it seems like I need to. And then you just hope, because if your sign pattern is wrong, your gradient's wrong. And
yeah, I'll just comment. I mean, I agree with what you said. The comment that in the inverse problem setting, the immediately will require inverting something of the form A transpose A plus W transpose W, and that can be a big problem, as you know very well from the work you've done. And so there's still work there to do. And so the number of iterations, the question of how much of that you need to do to get sufficient accuracy is still practical importance, I think.
Yeah, I guess I'm saying it's a great question. I don't have a really good answer, and I think that's a big problem with what I'm doing, is that that's an algorithmic question you really do need to solve in order to do this correctly. And we'd like to use some of those tools, right, to check whether our sign pattern is right and then keep iterating if it's not.
So we go on to the next question then. This is also, I don't remember if this is Caroline or Claire.
I don't remember either, but I think that the question's fairly straightforward.
Yeah,
it's also a great question. I mean, it should be forefront in your mind, right? It's like, why are you only using these toy images? I don't know. We need to run the experiment.
I mean, I think it's really good to start with toy images so you get some interpretability of the filters and so on. So we're just curious. All right, so okay, I think somebody else needs to put this in their own words.
Yeah, this is Claire. I think it's really interesting thinking about when you talk about the CNN structure and also comparing how much of it comes from the architecture and how much of it comes from training data. And I was thinking whether we could make a parallel and say, well, how much of this sort of method comes from the cost function formulation versus how much of that comes from training data. And I wonder if that when you were comparing with the what you call unsupervised method, can I understand that's what you're trying to do?
Exactly, yeah. So I think that's a really nice point, and we should think about that. So, and Jeff touched on this also, right? So sort of implicit in the learned regularizer is that learning the regularizer in the context of a specific inverse problem gains you something. And there's reason to think that that might not be true, because if you go the sort of the statistical route, you say, yeah, that regularizer represents a prior, and so it only cares about X, shouldn't care about the measurements. But practically, we have a small amount of evidence now from the experiment that I ran that you do gain something there. So I don't know. I mean, again, it's a great question, and I don't know the answer exactly. It says, "What's my intuition?" Even that, I'm not. I guess what I can say is that I think we always kind of knew that there was an interaction between the regularizer and the A matrix. There's this feeling that you want the regularizer to kind of counteract the null space of the A matrix. And very high on my list of experiments is actually to do this, but change the A matrix and see if we can think about, well, first, do we get different regularizers? And then can we understand why we would tend to get different regularizers? That even I need to think about what experiment, what data would I use? What A matrix would I use to probe that?
Yeah, that would be very interesting. While we're on this slide, I don't know if you see my mouse. You commented about how one of these filters has got higher values than the others. And that reminds me of back here, I have one regularization parameter alpha, but we'd really like to learn in some sense, maybe different thresholds for each of the filters. And the nice thing with your L1 formulation is you essentially can bring beta inside, and the filters have their own individual thresholds, or equivalently, you scale the filters and have the same effect, right? So I think that's really one very nice thing about this bi-level formulation that you're using here, that you're getting that automatically somehow, I think. Do you agree?
Exactly correct. Yeah, okay. I think, if you were eagle-eyed in the presentation, probably that beta was sometimes there and then at some point disappeared. Right. And I probably should have mentioned, but yeah, I mean, it's homogeneous, so you could pull that thing inside.
Exactly. Yep.
Something that I've kind of dreamed about, though, is there's a subtle difference between saying, I want a W that works well on all images, and saying, I want a W that I can scale with a scalar parameter. I'd like to do that one too, because that's interesting. And you could potentially train on data with a bunch of different levels of noise.
Yeah, that's a very nice idea. Of course, in the machine learning literature or the CNN literature, it's very common to normalize your images before you put into CNN, but this bi-level thing doesn't quite have that same flavor to it. So what you're talking about would inherit some of that. So that's super interesting.
Yeah.
I think that it would be nice to give some of the audience members a chance to ask questions before we dig into some of the more theoretical questions.
Yeah, we can talk about this after.
Exactly. So I'm going to, as a host here, preempt ourselves for a moment and give other people a chance to ask questions. I actually see some things in the chat. Actually, I think that's a private comment to me. It's about organizational aspects, so never mind. Let me just open it up. I think anybody should be able to unmute themselves and ask a question. Oh, okay. So now I'm told that the question in the chat actually is to ask you. That somebody's in an environment that has background noise, so they didn't want to unmute themselves. Okay. The GAN structure that you presented, Mike, with a simulator is similar to what's done in GALES, generative adversarial imitation learning, from reinforcement learning and imitation learning literature, which I don't know about. So I guess this is more of a comment than a question. Are you familiar with those, or were you aware of that similarity? I was not, certainly.
Not that specific one. I know there's like conditional GANs and a bunch of other things that could do similar things. So I'm definitely not trying to say we're the only people to have thought about that idea. And thanks for pointing it out. I'll take a look.
Cool. Anybody else should feel free to unmute themselves. In the meantime, we'll proceed because we've thought of questions, and so we might as well, take this opportunity to discuss them with you. Yeah, so you mentioned there were some technical conditions in your presentation, and you rightfully chose not to dwell on those, but we're curious about
how you're judged them up.
What's that?
You're judging them up. I couldn't avoid it.
Right. So and because we're very interested in this, and we're thinking about these issues a lot and facing many of the same issues you are. So I think there is an assumption of full row rank here in this theorem, and we're wondering, in your actual experiments, okay, you had about 9 3x3 filters, I think. Did you face that? Was that condition satisfied, or maybe, I don't know if you checked, or maybe the algorithm worked and so it's okay. What are your thoughts about that in practice?
Well, okay, you're making me bring out dirty laundry. So I was worried about this. I checked. And there's plenty of times when you really shouldn't be inverting that matrix.
Okay, all right.
And what I do in the algorithm, which I think is totally a hack and we shouldn't do this, is, well, you just throw the thing into conjugate gradient. In fact, there's two problems that you face. One is that you have infinite solutions, but the other is that if you're not sufficiently accurate, you can't actually convert the KKT conditions. So I don't solve AX equals Y. I solve A transpose AX equals A transpose Y. So because I was just like, well, I need to get as close as I can to something, because otherwise you can't continue. So this is bad. Now, this is why I bring up the Tipshirani thing.
Right.
I think you want to do this all with pseudo inverses.
Okay.
And you would not have that condition. The Tipshirani thing is really, you can take any sizes you want for all of those matrices. As I understand it, it's possible I'm wrong. I'm happy to hear if I'm wrong, but this, I can flash it up again if anybody wants to look, but this expression with pseudo inverses will always work, which is very cool. And of course, the pseudo inverses always exist, right? There's no condition thing.
Right. Have you thought about the memory issues with an inverse problem where we're now, where A is not the identity? I'm actually not sure what you're pseudo inversing. I assume it's something involving the sort of Hessian of the problem, A transpose A, or A stacked up with W or something like that.
So yeah, the pseudo inverses don't scare me too much, because I think that you can do, there's iterative stuff that gives you those pseudo inverses.
Okay.
What scares me a bit is there's projections onto null space of stuff. Yes. Typically that would involve finding a basis for that null space.
Yep. Mm-hmm.
And how are you going to express that? However, I think that it's not as bad as all that, and it ends up being something you can also do iteratively. But that's why I'm not maybe too afraid of presenting all this. I mean, because I haven't published anything about this, right? But I think there's real work to be done there. And I really hope somebody does it, right? And it can be me, it can be somebody else, but like.
Okay, well, your group at least, Sai and others have also worked on blind methods where instead of just trying to learn the sparsifying transform from a population of training data, you recognize that the I'll say patient at hand today might have some features that are different than all the population of training images. So you might want to learn at least some aspects of the transform from the patient as you're reconstructing them, right? Not limit yourselves to those that. Have you thought about trying to combine these in some way? So I guess the lower level problem might have a blind, learning a dictionary or transform in it.
I haven't thought too much about it. I think it's an idea we've kicked around, and it's certainly flexible. There could be other lower level problems. So I think you're exactly right. I mean, the first thing I would try is like, hey, well, put whatever other regularizer you want
Mm-hmm.
in the lower level problem. You could probably still all do all the math. Eventually you wouldn't like it to be, you know, like multiple weeks of work to do the gradients, right? You'd want something that kind of like that. And I think it's not so bad. I think there's sort of a pattern, and yeah, I think this is doable.
Okay. I'm curious whether Sai is still with us, but I won't. Yeah. All right. So that actually, skipping from some of these planned. Oh, actually, Claire and Caroline, did we have any questions that I missed? Oh, actually, let's jump to this one. This is something we were curious about. For those of you who haven't seen the paper, at the end of the paper is a discussion of the broader impact of the work, which is quite interesting. I hadn't seen this before, and I actually think it's it could be trend setting, or maybe there's, in the same way reproducible research was a new thing several years ago and now has become, you know, kind of a best practice. Maybe this is a best practice that is emerging, or maybe you're setting the trend. I don't know. So I'm curious if you could just give me any background on this.
The background is that this was a NeurIPS submission, and NeurIPS actually requires this.
Okay.
But so it's certainly not me trend setting, but I do think it is, it's a nice idea. I don't mind it at all.
Yeah.
Always worth thinking about this. I don't know if, you know, I'm since you're putting it on a slide, I hope I wrote something that was at least reasonable.
Oh, yeah, absolutely. I think the highlights were our own, just some things that, I mean, this totally makes sense for NeurIPS to be doing this with all the concerns about AI and equity and bias and all these things. And we don't tend to worry much about that in the medical imaging world, but well, maybe you would if you're doing classification, right? And things like that. But in the reconstruction world, we haven't worried about so much, but I think it's terrific that to have authors and all of us, and students included, thinking about this. So I thought that was worth pointing out, since at least to me that was new. I'll make one more comment myself and then see if Caroline and Claire have any, or anybody else has any other questions. So the one norm makes it for this interesting mathematical challenge of dealing with the non-differentiability, but I'm not sure that CT is the killer app for it. So there was a nice paper by Jean-Baptiste Thibault of General Electric when they were developing their model-based image reconstruction. And when they were first developing that for low-dose CT, they were using one norms or things very similar to one norms. And they showed the images of the doctors, and the doctors hated them. The patchiness that you get with that kind of sparsifying. Now, they were using finite differences, right? These were handcrafted filters, not learned filters. So an interesting question would be whether the fault was the one norm or the myopicness of the 1-1 filters. But they ended up rounding the corner, right? What's in the product that's clear in the paper is something that's more like a Huber function, or, you know, that kind of family. It's a generalized Gaussian something or other. And so, of course, that makes the problem simpler when the corner is rounded. In MRI, for whatever reason, people still often are using the one norm instead of rounded corners. At least the papers are written with one norms. Who knows what they're doing under the hood in the software. So that's both a comment and a question. So the comment is, you know, be careful about thinking about whether this is the right thing to do in CT. But I'm just curious, from your point of view, is this kind of mostly a mathematically interesting thing, or are there applications you're thinking about where you think the one norm really is the way to go? And so this is really crucial to develop this technology.
I think it's a great question, something I thought a lot about. It was one of the crises of this paper was kind of really looking, and as you should, looking at the related works and really thinking about those things and writing it out and saying, why am I racking my brain about this when, you know, I mean, it's all there. And in fact, you know, Gabriel Perret's paper, they kind of say, hey, yeah, we could do it with the one norm. It'd be really hard. So we relax it in this way. I don't know. That's basically the answer. Yeah. I've done a lot of little experiments and trying to see what really the effect is when you do that relaxation. And you can, I think we may have this in the paper, I'm not sure, but you can see that with the one norm, you get exact sparsity. That is, when you solve this thing, there are actually zeros in WX. With
right,
the others,
right?
Yeah, because there's a soft touch thing.
Right.
With the others, you actually get an odd thing where the actual minimizer, like you could never reach the actual minimizer, and you could. It's like it's like this. I don't know how to describe this any more than this, but the cost like goes down and asymptotically approaches exact zeros, but I don't know that that actually matters. And then quickly just jump into your CT thing. A folk idea that I have that maybe you've had is, I think if you took almost any image reconstruction paper and you took their results and you just put a tiny Gaussian blur, they would look better and they would have higher SNRs.
That's that right.
And I don't know if these things really connect, but I think that's why we like our ADMMs a little underbaked.
Yes.
And I think it may also be why we like smoothing our guys a little bit.
Your point that you never converge, yes, of course, with the lasso kind of problem, eventually it figures out the sparsity pattern, and then there's a nice solution to it at that point. I was going to make, but on the other hand, though, once you round the corner, often the lower level cost function is strictly convex, so the uniqueness issue goes away. But you're right, you never get there except asymptotically. So those are kind of trade-offs there.
I probably spent, I don't know, a couple of days trying to write these and compare, and I was like, yeah, you never get there, it's bad. And of course, you get epsilon close.
Right, exactly.
So when you look at the two things, they're identical.
Right,
I mean,
exactly.
It's kind of so.
Caroline and Claire, do either of you have any more questions? I don't know if I skipped anything.
Not specifically, but the previous slide you had something about splitting, which I'd be interested in.
Oh, you did skip.
About splitting?
WX sparse versus WX is approximately.
Yeah, that's why I was curious if Sai was still here. Yes, this is a kind of a terminology question, right?
Oh, geez. I have to check if Sai is here for it. Okay, before I speak about this, what specifically is the question?
Well, in your paper, you say, you distinguish. I have trouble distinguishing these two terminologies, right? So while I've got a disciple in the room, I thought I would ask. So, analysis sparsity, I think you say, is that WX is sparse, and then transform sparsity is WX is approximately Z, where Z is sparse. And I might better agree with that distinction if we put zero norms everywhere, but often we're putting one norms, which are not, strictly counting number of non-zeros anyway. So I just was curious what your thought was about this distinction. But if you'd prefer not to answer while it's being recorded, I'm okay. We can talk about it tomorrow.
On this one. Yeah.
What's that? You say you're in punt on this one?
Plead the fifth.
Yeah, okay, that's totally fair. I think you've answered the question. All right, let's see. Anybody else? Let's see here. Okay, now the seminar is organizing, telling me we're going long and we're really getting into the weeds. So let's collectively thank Michael very much for this really wonderful seminar. And I look forward to meeting you individually tomorrow and continuing this discussion. And thanks again.
All right, great.
So let me see. VJ, do you end it or I hit end?
Yeah, I end it. Yeah.
Okay. All right. Thanks, VJ.
Thanks, Mike.
Thanks again, Mike. Talk to you tomorrow.
Again.